Luis, Fala, brother.
Hello, can you hear me? Hey, how's it going?
Oh yeah, man. When we got Jared, Daniel,
What
where
up?
you at? All right, Mario, and the guest of honor that I am going to end up replacing myself with, Lina. Lina, you are the one who has been tasked with leading this panel that is coming up. I'm going to hand it over to you, and let's get it started. Thank you all for joining us. Oh, you're on mute though,
We
Lina.
can't hear
Just
you.
heads up.
Oh, I wanted to triple to you earlier. Amazing to have you all here. We're going to talk about cost optimization and performance. So I'm also an ML engineer, and I have an amazing panel for you today. So I have two people who run large language models in production. We have Daniel, who is a research scientist at Niva, which is an ad-free private search solution. Tried it, quite nice. And they're using large language models in search for all kinds of questions like summary, semantic retrieval, query generation. So I'd be super interested to hear what you learned by applying it to this large space. Then we have Mario, who is a staff engineer at Intercom, and they put one of these early GPT-4 powered projects out, which was a chatbot. And then we have two people from the tooling space. Really also very excited to have here Jared, which is the co-founder of Prompt Layer. Hey, Jared.
Wow.
Hey. It's a platform to manage your production LLM apps with reliable prompt engineering, monitoring of the prompts like versioning, cost, latency, and you can track historic usage history and performance. So I'll be excited to talk more about evaluation. And last but not least, we have Luis, who wears many hats. He is a professor of computer science in Washington and also the co-founder and CEO of OctoML, where they offer easy and efficient deployment. And the very interesting part to me especially was that you can just upload any computer vision or NLP model, and it will be optimized, and it will tell you which instance to run it on. And soon you can also run your models there. So I'd be very interested how you help users to make these models run very more cost efficient and faster. Okay. So maybe let's start with costs. We know generally running large language models is quite expensive, much more expensive than normal paid backend APIs. Mario and Daniel, maybe because you run it for products, was cost an issue? How did you approach this, the cost angle of running in production?
Yeah, so cost is an issue, especially with scale. And I think that's kind of like where we started out. We started off with some of these kind of like foundational APIs as a way to figure out, is this a product that's useful? Does this help our ranking signals? Do our users like this? And then once we actually started getting that, both the cost of running that and how much we could run this on really becomes a bottleneck. So if you think about like summarization systems, potentially running it like in production real time for users, that's very possible via API. It's kind of slow, it can get expensive, but what if you want to run summaries on, let's say, the entirety of a web index, which is on the order of billions of documents? At that point, no longer can kind of become actually cost possible, so you have to move in-house to some type of smaller system. And at the same time, it's just a question of like, how widely do you want to cast the net when you're using these models? How many people do you want to access them? And what is their expectation for turnaround time?
Yeah. Do you have a guideline? Like how long would you start? So you have a working prototype, and also maybe could you speak on, imagine you're running it in-house now, but it's still expensive, right? So do you have a ballpark compared to other services? How do you evaluate that, and how do you bring it down to which level?
Yeah, so on the evaluation side, or initially using kind of these foundational models, it's about kind of like having rapid iteration and the ability to kind of refine things via prompt and get this in front of users to actually kind of figure out what they're thinking. And once users are actually saying like, oh, this is great, this is the use case that I'm working on, then we tend to kind of focus in and figure out how can we distill this, extract this into a smaller model. Within these kind of smaller models, the process we generally think about is less around just the dollar cost, more on kind of like, where can I run this? And for us, the golden threshold has been, can we make this model run on a single A100 GPU, A10 GPU, or on any type of CPU requirement. Because like when you move from the A100 to an A10, say you're serving AWS, that moves you from having to pay $40 an hour because you have to get 8 at them at once to on the A10s, you can pick up a spot instance for 30 cents. And so like at that price point, you can do pretty much anything. And then if you even move it to CPU, the game changes even further where you can move to kind of billions of items without necessarily even thinking about this. And so a lot of our work, we're moving like for some of our semantic search, these are small query encoders. These are 30 million, 40 million, 100 million parameter models. And so in that case, we can actually run the query encoder on CPU. So it sits in the same system that's actually doing the retrieval. And so that can just simplify production. It's just a question on really like figuring out what scale you're going to, what is your latency throughput that you're looking for, and what is kind of the size. And one of the things that we saw was the foundational APIs are actually really slow. And partially, that's actually really good because it changes user perception. Whereas like before, people's perception via Google search was like anything over 100 milliseconds is terrible. Now people are used to waiting 3, 4, 5 seconds. And we've been able to see that we can take, if we're running Cohere, we're running OpenAI, what's it called? I'm totally sorry. Anthropic. They're on the order of like 3 seconds for a response for a single batch. We can get a model that is 20 billion parameters to respond in 400 milliseconds. So that like net improvement in speed is huge just by bringing it in-house. And that's just because you don't have to go on the internet. It doesn't have to go through their orchestration. You can deal with your own. And then the other thing is, when you bring this in-house, you really become a master of your own fate, where one, any type of latency optimization is actually owned by you. You don't have to worry about API rate limiting. You don't have to worry about like their entire system going down. I think that was actually one of the things that really pushed Neva to bring these things in-house, because sure, OpenAI has 99% uptime, but that's 99% for everyone. That was not what we were experiencing at all. And when we're trying to deliver this product and we're like, well, this use case doesn't work because their overall system's down and we can't do anything but sit on our hands, it really gave us kind of like the impetus to bring this in-house.
Yeah, we experienced the same issues. We also had they were regularly not available, sometimes 50 minutes at a time. So that was a problem. Okay, anyone else on cost consideration?
Can I just jump right in here to say, hey man, like I love what he just said, Mario. Like this is exactly our point of view, is that hey, often you don't need the highest end hardware, right? So you can live with hardware that actually hits your latency and throughput requirements. You know, even though there seems to be a strong, let's say, shortage of high-end silicon, many people don't realize that they probably don't need high-end silicon to deploy their models. And you know, basically what OctoML offers is exactly what you talked about, but in a general way, in a fully automated platform for broader users to deploy their own model, their own custom model, or an open source model in a platform that they control, automatically choosing the silicon for you and turning models into high performance, portable artifacts and code that you can run on different hardware. I just want to say, you know, we should definitely follow up after this because our view of value here is 100% aligned. So, but in panels, we need to disagree with each other. So somebody should disagree with him to make this interesting, right? So
you can disagree about the most promising ways to go about cost reduction. So if you each had to name like your top 2 methods, because you can do so much, right? If you start reading on the internet, what are the top things to do to reduce cost? You have a list of like 20 items. So maybe you can disagree on that. Let me give me each your top 2.
Okay, so since I was going to say 2, first of all, pick a model that does the thing that you need and optimize as much as you can, because then you have better performance in a given target. And then second, choose the right silicon for it, the one that has the lowest cost possible and hits your performance requirements.
So you're also saying a different model type, like a smaller type of model.
Exactly. Pick the right model, optimize as much as you can, hopefully automatically, and then to pick the right hardware for it. So
yeah, my 2 things would be kind of like structured pruning and knowledge distillation, where you can take the large model and then you actually just remove portions of it until it fits in whatever systems you have. And like direct example for this, like we're serving a FLAN T511B parameter model that physically doesn't fit in an A10 GPU until you remove at least 60% of the weights. So you have to, just because like the actual size of the model, once you've done that, you can make that model fit in that smaller GPU, but then you have to use some form of knowledge distillation so that the model doesn't actually have this like decrease in quality. And generally speaking, those 2 things together really provide like big performance improvements. And if you get really crafty with your distillation, and I used to work at Neural Magic, which focused on distillation for CPUs and everything else, and we were able to get 30, 40, 50x improvements on text classification tasks by basically just pushing in that like knowledge distillation as far as we could with the biggest teacher model and the smallest student model, and that just works extremely well. The downside to it, I guess I'll take my own, going against myself in the other corner. There's a non-zero cost to actually moving all these things in-house. Like if you think about the beautiful part about these foundational models is the feedback cycle is super fast. So if you think about like, say you're doing something with a prompt for search engines, you want to rephrase how your system works. And so you just change the prompt and it runs. It's good. It's in production. It's good to go. If you want to do this in-house, you basically say you want the system to take a more neutral tone. You have to go through all this iterative approach to make data sets, distill this data set into something smaller, take this model, compress it into something smaller, figure out how it moves to production. So like your iteration time goes from being on the order of minutes to potentially days or weeks. And that's kind of like this like nice trade-off of like, how much do you want to explore? How quickly do you want to be able to iterate on products with customers, to how quickly do you want to be able to optimize and control your own fate?
If running in-house, what do you say, what size of team do you need just for the ops side of running, I don't know, a few models? Or let's say 2.
It kind of
I guess it depends what, maybe it's too general a question, depends what type of model probably, but just maybe can you give listeners like a ballpark on the amount of work that you had to do?
So I would say that bringing these models in-house and making these models, there's about 4 of us that were working on anything from data modeling to, I'm the compression guy, so that's what gets me up in the mornings. But there's other folks who are working on the modeling side and otherwise. I think overall at Neva, directly working with models, there's probably around 10 of us.
Okay. And Mario, Jared, thoughts on the cost side?
I can maybe give like a little bit of like a few thoughts on how you can control cost before you actually move anything in-house. So we don't really we don't train or fine-tune LLMs ourselves. So right now we are pretty much on the consumer side, just calling our APIs. And it's tricky, it's expensive, and I think even DaVinci can be a very expensive model, depend how you use it. And most of the time, like we just first do pretty much feasibility exploration of, is it possible to do what we want to do? In some like really isolated cases, like can we summarize one conversation, for example? And to assess that capability, we would take the best model first, probably see whether that's possible, and like try to go down, just try to pare down the model to the lowest model that gives us results that are okay. Like Daniel mentioned, that's often like, I think, producing games 25 years ago where everything is too slow and you're totally like limited by how much you can process. And it kind of like cuts both from like cost and latency perspective. Like you just can't summarize all the conversations in Intercom because we'll bankrupt straight away. There's like too many of them. So, but like one thing that's interesting for like cost reduction is just basic engineering thing, which is just call it less. And that's not always possible. Of course, I think like probably like in Daniel's case in Neva, that's a little bit more tricky if you're doing semantic search, but like the systems we build are usually a complex set of things that talk to each other, and there are multiple components that are implemented with LLMs. And sometimes you can put like a really simple classifier before doing something to figure out whether it makes sense to call LLM at all. So like that's one technique that I think can work quite well, because not all tasks are. Sometimes you can find a tool that's really simple and is going to be able to say whether the more complex and smart tool is going to has any chance in finding an answer. So I think like that's one technique that helps a lot.
Yeah, and I just echo Mario's first point there that like the first step, you could do these bringing it locally or whatever. But if you're using these large foundation models from OpenAI or whatever, the first step is just knowing what's going on and kind of just building version 1 and kind of just understanding how the cost works. And this is like, it's a bigger step than you'd expect, and just understanding which prompts in your system, which parts are expensive, and like knowing where to go from there is pretty important, actually. So just echoing that otherwise.
Yeah, so there's some great tricks you can employ when starting off, and then maybe later when you scale to bring it in-house. Okay, let's talk about latency. It's
Oh, can I just add
Sorry.
one more thing? I think one thing that I think was implicit, but I don't know if it was said explicitly, was, you know, there's plenty of open source ready to go models that can do. I think Daniel mentioned, you know, T5 Flan, for example, they can refine for users. I think people realizing that you do not need to pay the OpenAI or Cohere tax if there's a use case that you know an open source model can do well, and you can run much more efficiently in a platform that you control, that you might not need to build on your own. That already gives you a very, very significant room for cost savings there, right? So just know your use case. You don't kind of like, there's an analogy of use a CPU because it's general, but a CPU is expensive, but then use a GPU to do the bulk of the computation because that's more efficient. I think there's a direct analogy here where you have these, you know, general expensive models like GPT-4 that have to pay to use, but then for things that you know that you want to do and you can specialize it and use an open model, you're probably going to pay a lot less, by probably orders of magnitude. So
just to make it interesting and push back a little bit, I'd actually say that
Please.
if you're, yeah, the way I see it, if you're, I mean, it depends where you are in the stages of development. If you're building version 1, if you're trying to ship something where, honestly, most people working with LLMs today are trying to ship version 1, I'd say don't bother with open source models. Get something working on GPT or
100%.
something. Yeah.
But
So
once
we're
you
on
know
the
your
same
use
page.
case, on the same page. Yeah, but just like, hey, if you're writing code here, you write on the CPU, you make sure it works, and then you upload to the efficient compute unit that does what you need to do. Similar thing here, you start simple with a model that, you know, is more expensive, and as you understand what you actually need from it, then I'm fairly confident you can find an open source cheaper model that does what you need to do, right? Question answering, summarization, and stuff like that. Right?
I think the part that's important to consider in the cost reduction also just is staffing a team. Like the story I have here is I've always worked in like the search world of like big search engines. So there's always been a lot of money behind this. There's teams, everything else. My brother used to work at FineTech, and at some point they were looking for something that could classify businesses. And when they poked around and figured out like, what would this cost to have our own system? You have to hire people. You have to hire at least one ML engineer, probably an infra engineer, and you actually have to run it. And pretty much their bottom barrel cost would be on the order of, I don't know, $500,000-600,000 a year just for like the team. And they could make 99%, like what Alex was talking about. But in reality, they just needed something that was 70%. And like, if they just plugged it into a system, they never had to hire an NLP team, and they never had an ML team. They had the system that was beautiful because like they could go in and someone who could just tune the prompt until it works well enough. And it just like, by using this large system, they saved money because they didn't have to hire expensive people like me. Yeah. And it's understanding the use case because they were only pushing 10,000 examples through the day. So like their cost is not as high versus on like a search engine side, or when you're like dealing all the interactions that Intercom has. Like if you wanted to do all the summaries, then that kind of cost calculus change.
Yeah, it's a question of scale. So clearly, if you use it like the Excel plus type of thing with a human in the loop, then using it as the API will be always more cost efficient. It's a good point. Yeah. Okay, so moving on to latency. This is another huge problem. So just getting, or maybe I'm a bit, spoiled from normal classification models, but just moving into the LLM space and seeing that just one token takes 0.7 seconds on P90 was shocking. And then normally you need like a whole sentence. So that can take several seconds. And how do you deal with that if you have a user, on the other hand, who is like normally very impatient, thinks after 1 second the application is broken? What are typical, how do you go through the life cycle? When do you start out maybe not looking at speed? What types of speed ups can be, are possible to expect? Do you do this trade-off between model size and speed, or like how are you thinking about this? And maybe also throw your best tips, like if you can do 1 or 2 things on speed, what do you do if you don't have a lot of time, literally?
Yeah, I can walk through a direct thing that we did in Neve and we've talked about is our initial summarization model. And initially, use a large language model, you do the summaries, you're basically looking at about 3 seconds per item. And we're doing a batch of 10, so we're basically looking at 30 seconds. We did this and figured out that, like, oh, turns out this is actually useful and very good. Iterated our prompt, and then brought this into a smaller model in-house, distilling into a T5 large model. But serving that on like a batch size of 10 on an A10 still took like 8 seconds naively. So then kind of we went about all these ways. So first off, there's a great library called Faster Transformers. NVIDIA kind of supports it. They don't fully support it. So like you got to fiddle with it a little bit. But just moving from native PyTorch serving to Faster Transformers basically brought us down from like 8 seconds to like 1.8 seconds. So huge gains just on changing how it's served. It worked on the GPU. Had a funky build process, but it worked super well. And then from there, we threw in some notion of structured pruning and asymmetrical pruning on the encoder-decoder side, just because like the encoder produces this contextual representation on a sequence model, and you want the best contextual representation possible. And it also only runs once, so the cost is pretty much doesn't matter, versus the decoder runs again and again and again. So we heavily compressed the decoder. So we basically took this model that started off with 24 layers on either side, and brought it down to 24 layers on one side and 4 layers on the decoder. And that meant that like by the time that we were done with Faster Transformers, this compressed model, we got down to roughly like 300 milliseconds for a batch of 10, which that allowed us to basically say, hey, it now will cost us $20,000 to create a summary for everything in our index. And we can actually do that because we like decrease these costs versus when it was 10 seconds, 30 seconds, thing just not tractable.
Yeah. I just wanted to underscore making sure to use the very best kernels, the very best binaries for the given hardware that you're running it on, because that's stuff you can do without changing your model at all, or any batching parameters, any other system parameters. Start with that and see how far you can go. And the problem is that this is dependent on the hardware target, very specific on the hardware target. So the more you can automate that, the better. I'll put a plugin for what OctoML does. We can help you search automatically for what's the right library or compiler using TensorRT or TVM or cuDNN for NVIDIA or the equivalent for other hardware targets. And then after that, change the batch size. Sure, you might pay a little bit more hardware utilization, but if latency really matters to you, reduce the batch size, pay a little bit more. So
I'm really happy to hear. Sorry, go on.
Yeah, Mario.
I'm really happy to hear like what Daniel and Louis are talking about, because like if you're in our world, we're just talking to some external API, your hands are so tight. So effectively, you have like 2 ways to improve the latency. One is by shared capacity, if they can give it to you, and then you can play a little bit more with like throughput latency curve and like where you want to sit there. And the second one is maybe like what I said, like if you're okay with not finding an answer, and if you can detect it quickly, maybe just don't call it and return the answer straight away. Like there are UX paradigms, like I think it's becoming quite for like chat applications, just piping the tokens directly from LLM to the user. So user is, saying straight away that something is happening, but sometimes you just can't do that. Streaming effectively, yeah, like streaming like directly from LLM to the end user experience. Like sometimes you want to check what's, the answer when it's fully generated, and in these cases, like you have to wait for it. And for example, for GPT-4 shared pool of capacity, like the latency I'm seeing is something like 100 millis per token. For English, it's usually 1 word per token. They change the tokenizer for GPT-4, but it's extremely high. So I'm really happy to hear what Daniel and Luis are talking about, because I hope we'll be able to actually move some of these things. Like once you understand like which use cases are actually the most important for us and which use cases make sense to optimize and bring in-house.
There's some tricks you can still do on when you call an API. You can work with a prompt, because the main latency is actually in the output, not in the size of the input. So you can tell it to be concise or give you back a number of paragraphs, like be a bit shorter in the output. So this is something, we can clearly see from the panel that if you want to be really fast, you need to move it in-house. But let's say you're in this first stage where you still need to understand the cost and the speed. There's a small amount of trick like semantic caching and what Mario mentioned that you can do. Maybe, Jared, you also have a dashboard where users can track latency they observe. Is there some insights you can share, like how do they, like what you observe in terms of your users with respect to latency?
Yeah, I guess the interesting thing here is what is the low-hanging fruit to kind of help with latency? You mentioned one is obviously like how long the response is, but the other one, which is also very obvious, but falling back to different types of models. So obviously, if you can detect how badly you need GPT-4 over 3.5, if there's a use case where you can fall back to 3.5, a faster model, or even something kind of although that might be the fastest one they have now, but or maybe Claude or something like that. Kind of there's becoming, in fact, there already is probably this whole axis of which engine do I use for this problem, as opposed to kind of just saying we're using GPT for everything, or we're using our in-house for everything. I think these are all tools that have pros and cons, and one of the pros and cons of each is latency.
Yeah. I can't resist bringing up again, like one thought that was mentioned very briefly, Lina, that streaming the output, like I'm more on the user side these days, interacting with these bots. So they go and buffer the entire answer before they show it to me. A simple thing that just helps human patience is to say, it's being typed, or streaming it to the user, because then you see that something's happening, right? So I hate interacting via Slack bots here. It buffers the entire output before it shows it to me. Like if you just said, hey, the bot is typing, just let this GPU work hard for you, that will already go a long way. So don't change the latency, just manage human expectation. They will probably go a long way as well.
That's such a good point. The actual UI experience. There are some drawbacks in terms of like safety of the response. Like if you stream it, you can check the response. So that could be a concern for some type of applications. But I like your second idea of like typing, like when you see someone typing in some different types of like a human, I don't know, different chat applications, that helps. You see they're typing. It's a good idea. Okay.
Yeah, I think just I'd add real quick. Yeah, I think there's a lot of UX ways to do this, to solve this problem. That's one thing. And then also just one other addition is these latency amounts of like GPT-4, these latency amounts of the models being offered are not constants either. We've like been looking kind of at our high level like user data, and the latencies are like very spiky of things like GPT-4 and like it's very laggy some days and not other days. So if you really care about optimizing, that's probably another thing to look at.
Yeah.
Yeah.
That's definitely an issue. They don't support any SLAs yet, so I guess that's hopefully soon to come.
We'll be having a latency page to kind of help with that soon, so stay tuned.
Yeah. On that, something we talked about earlier, I meant to, is like batch sizing is hugely important, both for like the streaming component, but also if you think about like when you're actually doing this like greedy token by token decoding, if there's any difference in the length of each batch, everything basically defaults to the longest batch. So like there was some literature out of Washington, I think, that in machine translation, they found there's like 70% of tokens and batches were effectively useless tokens because it was driven by the longest padded sequence. And so like, especially if you have a high variability in your outputs, doing anything but a small batch size can like be bad, because it's like if you have a short response, you don't get to enjoy that. Basically, all your responses are limited by your longest output.
Makes sense. Do you control for that in your prompt somehow, or how do you handle that, the control of the output size?
I'd say on our side, we've done a bunch of optimization there, even as you mentioned, on like making the GPT-3 output more concise, which then we kind of can distill from. But it's really just kind of fiddling around with it. Like one of these things that we saw was with this kind of asymmetric pruning that we did, when you move the batch sizes larger, all these gains went away. And that's because like when it was smaller, you really could like highly optimize it because you're not waiting on this decoding, versus when you have a large batch size, you're just basically dominated by the longest sequence. So all your compression is completely kind of just broken.
Interesting. That makes total sense. Okay, let's talk a little bit also about monitoring. I'm very curious what you guys found useful, both like human-based, LLM-based modeling, any other type of techniques that you found useful.
I can jump in here with like a high-level overview, and I know I've talked to Mario personally about this. I'm sure he has some things to add too, but kind of what we've seen our users doing kind of breaks down into three big categories. First category is, which I think is the real source of truth, is the end user giving you a thumbs up, thumbs down. Or you can use behavioral based, maybe like clicking refresh or closing out is a thumbs down, is a negative signal on like how the prompt is doing. That's one category. Another category is this whole MTurk hiring out to click workers to do. Very boring way to do it, in my opinion. Then the third category, which I think is really kind of where the future is here, is synthetic evaluation. So how do you actually use an LLM to rate how good it is? And the one interesting thing I'll add here, which is kind of a thesis we're developing based on our conversations at ProbLayer, is kind of via negative is the right way to do this. Instead of trying to understand which prompt you have, how good they are, it's better to reverse the problem and say, how can I evaluate what's failing in prod? Which users are getting bad results? Like, is the chatbot being rude is kind of the most trivial example of this, but that's the way we see it.
Yeah, to be direct on that we're calling this critic modeling, and it works extremely well, especially with the most recent models. We found that, so like on a 7-point scale, the GPT-4 is off by an average of 1 label, which I used to do a bunch of human evaluation. That's pretty much the best you're going to get off like MTurk trained judges, and it works across fluency, accuracy, other things. The one thing here is there's huge positional biases. So we found that if you ever try to compare two things, the outputs don't work as well. So it's best to try to focus on individual comparisons and then potentially using some like weak supervision signal to figure out pairwise things.
Can you give us a concrete example when you mean critic? Like, what is the prompt you're giving the critic, or how does it work?
You're writing a thing of, hey, engine, your task is to evaluate how good a summary is for something. You are evaluating in a term of accuracy. Something that is completely accurate has X characteristics is a 7, something that is slightly missing something is a 6. Provide all your description of labels, give it to the model. The model will respond pretty damn well. But I will say, like the caveat, don't try to say, hey, I have these 2 summaries, which is better, because the model will, there's position bias. Depending on what you put first or second, the model will favor what's last. And at the same time, the outputs aren't as usable. It's kind of like the old Costco thing where you never ask someone why they prefer something, because if you ask them to justify it, then they will not actually give you their preference. They will give you an answer which they can justify. So don't ever ask the model to justify.
Yeah. Okay, interesting. Recency bias. It's also known in human decision making, by the way. Like if you give a verbal statement of choices, people just forget, very similar to what we observe in the network, the first option and tend to pick some of last in decision design. Very interesting behavioral research. Okay, anyone else on monitoring and performance evaluation?
Yeah. So just on the other side, we've done a bunch of stuff in-house, and we found, similar to what Jared mentioned, where like the tail latencies can get very out of hand, where you can see massive spikes, and they can be caused by these weird corner cases that you never thought of. Like we were seeing massive tail latencies occasionally, and that turns out we were running a model on a sliding window, and occasionally it hits super long documents. And like the solution was like, oh, what do you do? Just truncate after, I don't know, 10,000 tokens. Mm-hmm. But sometimes, and the only way that you'd see this is like, you look at what these outliers are. And in most cases, anytime we've seen an outlier, the solution is super simple. It's just like, oh, we didn't know about this weird behavior. Yeah. This is the easy fix. We no longer have that.
I call this terrible, I have a worse name, but I call this terrible experience debugging, which I regularly do. I was in recommender systems. So I also monitored like the really bad experiences, and I just picked one every week to deep dive on the root cause. This is very similar to you saying like monitoring the bad experiences, like the edge cases, the long latency, and then you find like groups of problems that you can fix one by one. Very good. Okay, cool. I think we're out of time.
I just wanted one more thing, if you don't mind. Just so putting a plug here, come try the OctoML profile. Lets you, with a single line of code, you can get your model running across different hardware, and you see the profile of the latency it takes for different options and so on, to give a very detailed, actually running the model and profiling it for you. So love to hear from you. So
yes, please try out the interesting components.
Can I just jump out? Can I jump in for like 30 more seconds? Like I'd be interested to hear from others, like probably in chat, like how they deal when labeling becomes too expensive as well. If you need like GPT-4 for labeling, then it's expensive again. So whether people have like some smart sampling techniques or maybe like pre-filtering initially, are there solutions out there for that? It seems so nascent field to me that pretty much like all the tooling is just in the process of building. So yeah, I'd be happy to hear in chat of like what people use for things like that.
Excellent.
Snorkel.
Yes.
Snorkel.
There you go. Oh, that's awesome. So we will continue this conversation in the chat. Yeah, please let us know what everyone is thinking. And thank you so much. All of you were
you.
incredible. And these are very poignant questions. And I really think that you all educated us a ton on how you're going about it and what kind of best practices you've found thus far. Wow. All right. I'm going to throw
Lina.
you all off stage now. See you later.